Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. I welcome you all in class of real analysis by Walter Rudin. In last lecture we have covered question number up to question number 5. In today's lecture we will start from question number 6. This question is very rigorous and has a deep concept of monotonicity, supremum of a set. This question has 4 parts. Inshallah, I will discuss each single part, and after today lecture, inshallah, you will completely understand this question. The question can be stated as for a fixed real number b, where b is greater than 1. The first part says if m, n, p, q are integers such that n and q both are positive integers, and this rational number r has a two rational form m over n and p over q, like 1 over 2 and 2 by 4, both are the rational forms of a single number. So here r has a two forms m over n and p over q. We have to show that the nth root of b raised to power m and the qth root of b raised to power p are equal. Hence, it makes sense to define b raised to power r is equal to b raised to power m whole power 1 by n. So, firstly, we discuss its first part, then we will discuss its second, third, and fourth part. So, in theorem 1.21 guarantees. What was the theorem 1.21? Theorem 1.21 says that the nth root of any positive real number x is unique and it is equal to some positive real number y. If x is any positive real number and n is any positive integer, then its nth root always exists and it is unique and it is equal to positive real number y. So this theorem guarantees that the nth root of b raised to power n and qth root of b raised to power p must exist. But our target is to show that this nth and qth root are also same. Theorem 1.21 guarantees that nth and qth root of the expression b raised to power n and b raised to power p exist respectively. We will show that it is unique for nth root of b raised to power m and qth root of b raised to power p. As it is given that r has the two rational forms m over n and p over q, these are equal to rational number r. So by cross multiplication, we can write m times q is equal to n times p. Say this is my equation number 1. Now I will solve the nth root and the qth root of the numbers b raised to power n, b raised to power p. So consider we need to show that these two expressions are equal. So we will take them as equal and just by putting the values of mp, by putting this relation to remove the roots from both sides, as you can write it as b raised to power m over n is equal to b raised to power p over q. So to the denominator of both rational number is n and q. So to remove the roots from both sides, I will take the power nq on both sides. So by taking the power nq at left and right and then cancelling out the nth root, we have b raised to power n whole power q and b raised to power p whole power n. By cancelling q from here, this becomes b raised to power mq and this becomes b raised to power np. As it is given that mq is equal to np, so substituting np with equal to mq, this gives the equality. So equality holds. Further we have to show that this makes a sense for any rational form of r. Further, no matter how we write the rational number r as m over n or p over q, the expression b raised to power m whole power 1 over n always gives the same result. So b raised to power r is well defined. So this is the first part, and I hope it is very easy. Next, in the second part, we have to prove that this is the actually law of exponent. This is law of exponents. We have to show that this law of exponent b raised to power r plus s is equal to b raised to power r into b raised to power s hold if r and s are rational numbers. Actually, in this part, the author wants to show the laws of exponent also hold for rational number just as they already hold for integers. As here r and s both are the rational numbers, so suppose r is equal to m over n and s is equal to m dash over n dash, where m dash, n dash are all the integers and the denominator n and n dash are non-zero. So by adding r and s, we have m over n plus m dash over n dash. By taking LCM, we have the expression this, and by solving b raised to power r plus s, we have this expression. This expression can be written as in the form of the root 1 over n into n dash. Now this inner term, I am applying the law of exponent for an integers because this is the sum of integers and the law of exponents already hold for integers. So I can break this sum as b raised to power m into n dash into b raised to power m dash into n. Separating the terms because the roots, by the existence of root, I can separate the root of this product m into n dash whole power 1 over n into n dash b raised to power m into n m dash into n into this. Again, by using the theorem 1.21 that guarantees that its nth root must exist after cancelling n dash and n from here. So this can be written as b raised to power m over n, and this can be written as b raised to power m dash into n dash. But my m over n, this is a rational number r, and m dash into over n dash, this is my rational number s, which is required to prove. C part. This is interesting and have some deep concept. If x is a real number, define the set bx to be the set of all real numbers b raised to power t, where t is a rational number and t is less than or equal to this real number x. Here you can notice that x is a real number and t is my rational number, and it is also given that this rational number t is always less than or equal to this real number x. I have to prove that this set b with the rational number r has a supremum b raised to power r, where r is a rational number, hence it makes sense to define the supremum of this set for any real number x is equal to b raised to power x for every real number x. Actually, in the first part, we have to define a set. We have to define a set b of x. Then we have to show that this type of set, which is equal to this set, consists on the numbers b raised to power t type, where t is a rational number and t is less than or equal to some real number x, and t is a rational number. I have to show if I stick x to a rational number r, then this set b of r always have a supremum which is equal to b raised to power r. And lastly, I have to show that this definition also has a sense for any real number x. So firstly, we define this set. Let us write the set b of x is equal to b raised to power t, where t is a rational number and it is given that this rational number is less than or equal to some real number x. It is given that b is greater than 1. This is given in the start of the question. Our b is fixed and it is greater than 1. for these values of b, it is clear that the function f of t is equal to b raised to power t is a monotonically increasing function. How can we define increasing function? You know, a function f is called increasing function if x1 and x2 are the two elements of the domain, and x1 is smaller than x2, then the value of f at x1 is always less than or equal to value of f at x2. Then in this case f is called monotonically increasing function. In other words, the output at a larger pre-image is should always greater than the output at the smaller image. So if you take any value of b which is greater than 1, suppose my b is 2, then at a larger power of 2, suppose 2 raised to power 5, and other is 2 raised to power 7, which will be greater? Clearly 2 raised to power 7 is greater than 2 raised to power 5. That shows this function b raised to power t, this exponential function, is always a monotonically increasing function for this value of b. Now it is given that t is less than or equal to x. So for any rational number r such that, we choose a rational number r such that my t is less than or equal to r. So this shows my t is smaller than this rational number r. So by monotonicity of b raised to power t should be less than or equal to b raised to power r. This shows that for this set b of r, which is equal to b raised to power t, where t is a rational number and this is equal to some rational number or some real number t, this set has a supremum or the larger number which is greater than or equal to every number of this set is b raised to power r. So the number b raised to power r is an upper bound of this set. Next we show that b raised to power r is actually the least upper bound. You know, least upper bound means supremum, and I need to show that this set has a supremum b raised to power r. To show that b raised to power r is the supremum, I will use the contradiction. I will take any real number y, and I will claim that this y is less than br, and at the end I will show that there exists some number b raised to power t that is actually element of this set. This number lies between y and b raised to power r. That will show y cannot be an upper bound of this set. For this, to show that b raised to power small b raised to power r is the least upper bound of this set, let y be any real number such that y is smaller than b raised to power r. We will produce a rational number t less than or equal to r such that b raised to power t is greater than y. That shows no number less than br can be an upper bound of br, hence br is the least upper bound. In other words, there exists no real number between these two numbers, hence y cannot be an upper bound of this set. It shows directly b raised to power r is the least upper bound. So to define y, I am using the definition of logarithm. We define a real number s such that s is equal to log of y at base b. That can be written in form y is equal to b raised to power s. Next, by using the density theorem or density of rational numbers, what is the density theorem? Density theorem says that there exists a rational number between any two real numbers. So there exists a rational number t between two real number s and r such that this is my rational number t. This lies between two real number s and r. Now by using the monotonicity of the function, because b raised to power t is an increasing function, so its value at larger pre-image will be larger. So this shows b raised to power s is less than b raised to power t, and b raised to power less than t less than or equal to b raised to power r. So by combining these inequality as b raised to power s is equal to y, this shows that y is less than b raised to power r. I am just using here the density theorem, which says there exists a rational number between any two real numbers, and then I am using the monotonicity of this function. Monotonicity says that at a larger pre-image, the value of b will be larger. So b raised to power r will be larger than b raised to power s, but b raised to power s is equal to y. This shows that y is less than b raised to power r. This shows that y raised to power bs is not an upper bound. Since this result is true for every y less than br, this shows b raised to power r is the least upper bound of b raised to power r. Hence, the supremum of this set is equal to b raised to power r. In the C part, we have to also show that this definition of supremum has also make the sense for any real number x. Next, how does it make sense to define the supremum of this set b raised to b of x is equal to b raised to power x when x is a real number? We have seen this definition hold for rational numbers, as here we have shown this definition hold well for rational number. This definition also hold well for every irrational number. For example, if I take x is equal to square root 2, then the sequence of term, if you approximate the value of square root 2, this is equal to 1.4142 up to so on. So if I take x is equal to square root 2, which is clearly an irrational number, then the sequence of term 1.4, 1.41, 1.414 up to so on get closer and closer to square root 2, and consequently the rational exponent b raised to power 1.4, 1.41, 1.414, 1.4142 up to so on get closer and closer to b raised to power square root 2 and is bounded above by the number b raised to power square root 2. If you have this sequence of terms and I ask what is the upper bound of this set, your answer will be b raised to power square root 2. So b raised to power square root 2 is the upper bound of this set, or I can say that this sequence of terms is bounded above by this number. Since the set, it means this set b of square root 2 that can be written as b raised to power t, where t is my rational number and less than or equal to this irrational number under root 2. This set is clearly subset of real number r and is bounded above. So by using the completeness property of R, what is the completeness property of R? As R is a complete ordered field, the completeness property of R says any subset of R which is bounded above always has a supremum in R. So it means the supremum of this set must exist in R. So the supremum of b of under root 2 exists in R, and this is equal to the number b raised to power under root 2. This implies the definition hold for every rational number, and finally it hold for every real number x. And I can say b raised to power x is equal to supremum of b raised to power b of x. Question number D. This is also very interesting and something rigorous. In this question, I have to prove that the law of exponent hold for real number x and y. Actually, you can see here b raised to power x plus y is equal to b raised to power x into b raised to power y. So this is the actually law of exponents for real number x and y. Recall that we have defined this set b of x, which is equal to b raised to power t, where t is less than or equal to some real number x, where t is a rational number. This set has a supremum b raised to power x, where x is a real number and b is greater than 1. We will prove the result in 2 steps. Firstly, I will show that this number b raised to power x into b raised to power y is actually the upper bound of this set b of x plus y, and in a second we will show that it is actually the least upper bound of set. When I will show this is the least upper bound of set, clearly b raised to power x plus y, actually this is the element of this set. This is element of this set. Next, to prove that actually this can be break as b raised to power x into b raised to power y, I will show that this is actually, this number is also element of this set, and this is the least upper bound of this set, and both are the equal. So step number 1, b raised to power x into b raised to power y is an upper bound of this set. Let r and s are the two rational numbers, and r is less than or equal to x and s is less than or equal to y, where x and y are real numbers. By adding both sides, we have r plus s is equal to x plus y. By monotonicity of f of t is equal to b raised to power d, again using the concept of c part here. Monotonicity says that the power of b at r plus s is less than or equal to power of b at x plus y. Since rational exponent already satisfied exponent law that I have proved in first part, so I can break this term b raised to power r plus s, because r and s are rational numbers. So I can apply the law of exponent here. This can be breaked as b raised to power r into b raised to power s less than or equal to b raised to power x plus y. Say this is my inequality number 1. As by definition for real number x plus y, I can write this set b of x plus y is equal to b raised to power r plus s, where r plus s is less than x plus y, r and s are rational numbers. And by definition of this set, its supremum is equal to b raised to power x plus y, that is the real numbers. As least upper bound is always less than or equal to upper bound of set, so combining 1 and 2 we have, what is 1? My 1 is b raised to power r plus s is less than or equal to bx plus y, and this is my 2, which is supremum. Supremum mean least upper bound. So least upper bound should be less than or equal to this number. This is my b raised to power x plus y, which is the least upper bound. This should be less than or equal to this number, b raised to power x into b raised to power y. That I have to prove. This is my upper bound. Okay. Next, we show that this number b raised to power x into b raised to power y is the least upper bound of this set. I will use the same strategy that I have discussed in C part. I will suppose a real number k, which is less than b raised to power x into b raised to power y. I will claim that this real number k is actually the least upper bound of this set. Later I will show that there is a number between k and this number. There is another number b raised to power r plus s that lies between these two numbers, and this number is actually the element of this set. This will show that there does not hold any number between these two numbers, and shows that k is actually not the least upper bound. K cannot be claimed as a least upper bound of this set, and hence this shows the actual least upper bound of this set is b raised to power x into b raised to power y. Suppose for the contradiction that b raised to power x into b raised to power y is not the least upper bound of this set, and there exists a real number k such that k is less than this number, which is an upper bound of this set. We will show that this cannot happen, because as I am supposing here k is less than b raised to power x into b raised to power y, I am choosing a small positive real number epsilon such that whenever I subtract epsilon from these two numbers, the result also hold, that is k is less than b raised to power x minus epsilon and b raised to power y minus epsilon. By definition of supremum of set of this, what is the definition of this? What is the definition of supremum for this set? This definition says that if r and s are any two rational numbers such that they are less than or equal to some real number x and y, with b raised to power r is less than b raised to power x, the definition of this set b raised to power x says that the supremum of b of x is equal to b raised to power r. Similarly, the supremum of b of y, this will be equal to b raised to power this is equal to b of x, and this is equal to b of y. Now By using the monotonicity of b raised to power r should be less than or equal to this number b raised to power x, and b raised to power s should be less than or equal to b raised to power y. Like this, b raised to power r is less than or equal to b raised to power x. Now here I will use a very important result of real analysis. Actually, this is the inequalities of r. If a and b are any two real number, remember, if a and b are any two real number, I can find always a positive real number epsilon such that whenever I add this positive real number epsilon to the smaller side, the smaller side becomes bigger. You can take any real number. You can take any real number. For example, my first real number is 5 and other real number is 500. I can find our epsilon my epsilon is 501, suppose. Whenever I add this epsilon to the smaller side, my smaller side will becomes the larger side. So if b raised to power r is less than or equal to b raised to power x, I can find a positive real number epsilon such that whenever I add this I add epsilon to the smaller side, or I can say that if I subtract this epsilon from the larger side, the smaller side becomes bigger. So if I subtract epsilon from the larger side, this becomes b raised to power x minus epsilon. This will become less than the b raised to power r. Similarly, I can say that b raised to power s is greater than b raised to power y minus epsilon. Initially, b raised to power s is less than or equal to b raised to power y. So when I subtract this epsilon from the larger side, I can obtain the inequality b raised to power s is greater than b raised to power y minus epsilon. Multiply both sides, we have b raised to power s into b raised to power s, b raised to power x minus epsilon, b raised to power y minus epsilon. Using the law of exponent for rational numbers, rational exponents, I can combine this b raised to power r plus s greater than b raised to power x minus epsilon, b raised to power y minus epsilon. Combining 1, 4, 5. What is 1? This is my inequality number 1. b raised to power r plus s is less than or equal to b raised to power x plus y. What is 4? This is 4. K is less than this product. And what is 5? This is my 5. So combining 1, 4, 5, k is less than this product, and this product is less than b raised to power r plus s, and r plus s is less than b raised to power x plus y. From this inequality, I can write it as k is less than b raised to power r plus s, and b raised to power r plus s is less than b raised to power x plus y. As r plus s is a rational and its sum r plus s is, this sum is always less than or equal to x plus y. So this fulfills the definition of this set. It means this element b raised to power r plus s belong to this set, because above we define this set as this set consists of all elements of a rational exponent such that this rational exponent is less than or equal to some real number x. So here you can observe that r plus s is also a rational number which is less than or equal to some real number x plus y. So this shows that this number b raised to power r plus s is an element of this set bx plus y. So 6 shows that there exists an element b raised to power r plus s between k and b raised to power x plus y of the set. So this shows k cannot be an upper bound of this set. Because why k should not be an upper bound of b raised to power? Because an upper bound cannot be less than any other element of the set. If k is an upper bound, then k must be greater than this element. But if at the initial stage I have claimed that k was the upper bound, so it should be greater than this element b raised to power r plus s. So therefore no such k less than b raised to power x into b raised to power y can be an upper bound of this set b of x plus y. Hence b raised to power x into b raised to power y is the least upper bound of this set. And least upper bound means this is the supremum of this set. And combining it with 2, we have in step number 1, What was 2? The 2 was the supremum of this set we have supposed this is equal to b raised to power x plus y, and now its supremum we have proved this is equal to b raised to power x into b raised to power y, which is required to prove. So actually this question has a very deep concepts, and now you have I hope you have clear understanding. I have tried my best to discuss this question. So if you find this lecture helpful, kindly like, share and subscribe my channel. So see you in the next lecture. Take care. Allah Hafiz.